this video is for those who missed class in lesson 15, or if you just want to go back and review. I'm not going to write everything out. I'm not going to sit here and waste your time doing that. But I got everything kind of filled out, and then I just go through and talk about it, just to make sure you understand kind of what the things that we talked about in class. So the first thing that we need to talk about is the normal density function, the bell-shaped curve. This is what it is. I mean, this is the formula for it. So 1 over the square root, where sigma x squared, so these are the parameters, mu x and sigma x squared are the parameters. That's why there's a semicolon here, and then a comma in between the two parameters. And this sigma x squared stands for the variance from that population, wherever x is coming from, and mu x stands for the mean from that population. So the actual true mean and the true variance. Now, if it was, some books use sigma x. So if you want to use sigma x, that's fine. Just understand that's the standard deviation. You have to square the standard deviation in order to get the variance. Not a big deal. So everyone probably has seen this before, but what you might not have seen before is the natural log of it. So today we're actually going to need this natural log of this density function. So if you take the natural log of this thing, just like any other sort of natural log, you can break it into components. I'm going to break it up into this component and this one. So if you take and then put an addition sign in between them, let's see, there's the addition sign right there. And I'm going to go ahead. So I don't know, in class I didn't do this, but what we're saying is don't forget that this is just x squared minus 2x mu x plus mu x squared, and then remember there's a minus sign. This little minus sign is out here on the front of it, so it's just negative x squared plus 2x mu. Yeah, it's horrible. Mu x minus mu x squared. Right. So we're going to take these things, and that's kind of what's being done down there. So if I take the natural log of this, I know that I can bring a negative square root, negative 1/2 out in the front, because it's square root. This would be to the negative 1/2 power, so I know I can bring it out in front. So I get negative 1/2 natural log of everything that's inside here, which is what you get there. And then minus, well, when you take the natural log of the exponential function, we know that those are inverse functions of each other. So this basically goes away, and we're just left with whatever's inside the exponential. And that's why I did this real quick. So I can just take this thing and divide it by sigma x squared, and we get that. So you get minus x squared over sigma x squared plus x, right? The 2's cancel out, right? So the 2, I forgot my 2 in here, sorry. So there's supposed to be a 2 in that density function. So the 2's cancel off, and we're just left with sigma x squared under here. And then on this one, you get minus, and yeah, that should be a 2 as well. Okay. So that's what that sucker should look like. I think I got it right, and we'll find out later on if we did or not. So that's yeah, let me just make sure. Yeah, that's what it should be. So the natural log of this density function is this thing right here, and we're gonna need this here in a few minutes. All right. So what the purpose of today's class was to basically take this idea of assuming that the x's are from this normal distribution, and use that in our way to classify in a classification problem. So suppose right now, let's just suppose we have one predictor variable where p is equal to 1. I don't know if I said that or not, but p is equal to 1, and we want to determine if based on that one value of x, if it's one of these 3 classes. So you might have 4 pieces of data that's here, and each one of those are classified as 0. Maybe this is group 0, this one's group 1, and this is group 2, right? So I'm trying to classify the new x, right? So what happens when I'm trying to see, what should I classify that one as? And what is the technique? What is the number? How do we go about doing that? So the blue values in here represent the data that's all classified as 0s. The red ones are all the ones, and don't necessarily, I mean, this is not true that they would be separated out like this all the time. I mean, there might be a blue and run around over here, but it still could be classified as 0, even though it's above here, and that's okay. Just know that there's some kind of randomness that's going on in these, even when you make the assumption that it's normal. It is possible to get something, I mean, even out to infinity. It's possible to get, even if your true population mean was mu 0 and your variance was sigma 0 squared, then it is possible to get something way out here. Not probable, but possible. and same with red. You know, you could get a red that's running around in there as well. So if I had a situation like this where this is how the data was broken up, and I got a mu0 sigma squared, mu1 sigma 1 squared, and mu2 sigma 2 squared, we might not know the true population mean. We might not know or the variance of any of these. However, we do have data that's going to help us calculate what these are, right? So that's what you do. You just use the data, say, all right, all my zeros, I'm going to find I don't know, X bar 0, or I don't know what kind, but we're going to get an estimate for mu 0, right? And I guess one of the ways to do that is mu hat 0. And then we get an estimate for mu 1 using those data points. And then we get an estimate for mu 2 using those data points. So let's assume that we use this data, assume that it's normally distributed with this mu c sigma c squared, mean variance. The question is, how do we calculate the new data? And so we already know this. I already know the probability that x is equal to x given that, you know, the class is equal to 0, or y. We'll let y be our class. Y is equal to 0, and we can also do this one, right? So I can find. So how would I do that? Well, I would just use the density function, right? So I would just use that density function as an estimate for the probability. Obviously, if you remember, you know, that density is not necessarily probability. I'd have to give you an interval in this thing. So I don't want to get caught up too much in that, but just understand that we'd be using the density to sort of estimate what this thing is compared to, and remember, that's what we're trying to do, is we're trying to compare each one of these classes and figure out which one has the highest probability, in this case, which one has the highest density. So we have this. I have this in, you know, this is just the density function for this blue. This one would be the density function for the red. And if I kept going up, it would be the density function for the yellow if I had another one here. But that's not what we want. I don't want this one. I want to flip it, right? So what do? We use Bayes' theorem. So if you don't remember Bayes' theorem, go back and look at the previous video. I'm not going to waste time on that one, but basically there's a technique in order to flip it. So I want the probability that the class is equal to 0, given that that's your x. And so we know we got to find the intersection divided by the law. I mean, we're going to use the law of total probability here, and it's going to be equal to. So there's another way to do this, which is just using the conditional probability, and again, that's basically what Bayes' theorem is doing, at least the simplified version of it. And then you get that same probability that we already know, right? So the one that I can calculate, the one that we're going to call, let's see, this is blue, the one that we're going to call fx. Let's see, we're going to call that f. No, not x. We're going to call it f0x. And then we're going to call this one times pi 0. And then the thing on down here is, yeah, so that's the total probability for, I missed something here. Given y equals c times the probability of c. So I missed this conditional probability. It should be basically all of the entire, all of the intersections for this thing. So that's, I don't know if I should review this or not. This is also in the video on Bayes' theorem, but the law of total probability is the way we're breaking this thing up right now is that we got class 1, class 2, and class 3. And what's happening is I have some other event that's going on, and I want to know, let me make sure, this is class, let's see, this would be x. So that's x, and x is on top of or in this exhaustive list of events that could occur, right? So you're either going to be class 1, I'm going to be class 2, or class 3, and then I have this other event called x here that I'm trying to find the probability of. And so what it is that piece right there would be classified, or the way I would find that probability is it's x intersect y equals 1. Actually, I think I'm doing 0, 2, and 3. So 0, 1, and 2. And so that would be 0 then, which would equal to the probability that x is equal to x given y equals 0 times the probability of y equals 0. Okay, blow your computer up so you can see this as y equals 0. I know I had to write it really small. It's killing me. But that's that conditional probability there. Again, there's a video on this, sort of this, and then I would do the same thing with here, but it would be the 1, and I'd do the same thing to get that. And when you add up all these probabilities, which is basically what you're doing here in the summation sign, you're getting the probability of x. That's called the law of total probability, and again, that's just a really quick explanation of what's going on there. Let's see here. Oh, the last one, or the next one is, well, how do I find this pi 0, right? Because what I'm trying to do is figure out, well, what's the probability that y is equal to 0? So the way you do that is, just suppose we had 3 classes, 0, 1, and 2, and if you got no other information other than the number of, say, let's just suppose we had 5, we had 3 coming in here, and maybe we have 3 going, we would put another one, 4 going in here, without any other, so these are my y's, and this is the number of y's, right? The number of zeros is 5, the number of ones is 3. So if I had no other information other than the number of from each class, then I would just use a proportion. I'd just say this is 5 divided by, see, that's 4, 7, 12. So this would be 5/12, this would be 3/12, and this one would be 4/12. And these are called prior distributions. Why are they called prior distributions? Because they're just simply, and this is what you're going to do in the data, right? So I'm going to have some classification. I know in the training set how many zeros there are. I know how many ones there are. And so I'm going to use the prior distribution in order to find these probabilities. And that would be pi 0, pi 1, pi 2. Okay. So that's where you would get this, and we're going to call this pi. I think I've already called it that. Oh, I called it right here. And then all divided by law of total probability. I'm just going to call it LTP for right now. It's just this whole thing. And if you did the same thing with y equals 1, we would get, and what is it, red? So I'm going to come up here. I'm going to use red for this one and yellow for that one, right? So we got to calculate these suckers. And if I used red here, it would be f1x times pi 1 all divided by same exact law of total probability. We're still finding the probability that x is equal to x. And then yellow, that would be f2x pi 2 all divided by LTP. So the deal is, once I find the probability of y is equal to 0 given x equal to x and 1 and 2, then I have some sort of estimate for the probability. Again, remember, we're using the density for this part. I'm using the density function here, not necessarily probability mass function, but it gives me a relationship between these 3 numbers, and then I can just go back and pick the biggest one. So if you kind of read what's going on here in yellow, it says the idea is to classify the new x according to the highest probability. So all of the common terms can be left off. So what I mean by the common terms, I'm gonna go to white. LTP is in each one of these. So if I had 3 numbers, 5, 10, and 15, it wouldn't matter that I divided by 5, divided by 5, and divided by 5. Why? Because they're still going to be the same order. I would still pick this one because it would be 3 instead of 15, as opposed to this one, which would be 1 instead of 5. So the idea is you can get rid of all the common terms. Okay. Let's see, in LDA, okay, so I didn't talk about this yet, but this is the main assumption in linear discriminant analysis, is that we can assume that all of the classes have a common variance. That's what we're trying to do, and then we oh yeah, I already talked about this pi c. Oh, and then I even gave an example. So if you were to write out all of like y equals 0, x, and then say that it's proportional to this. Why? Because I got rid of the total probability of the probability of x is equal to x. I got rid of all those. So if you were to write them out, they'd look like this. Just, I mean, they basically bring them down. And then what I would do, oh, and then I got the sigma squareds in here as well. I want to take the natural log. So go back to the Jupyter Notebook. It does this in the Jupyter Notebook. But this would be pi 0. So natural log of pi 0. So I'm taking the natural log. So take the natural log, and you get natural log of pi 0. And then we know what this one is. Remember, I told you we're going to use it later. So it's basically just this thing with mu 0 and sigma squared substituted in. And if you do that, you get this thing kind of written out. And then if you do the same thing with mu equal 1 sigma squared, you get this one, and so on and so forth. And then we notice this, right? So if you see the red here, it says since these are the same for each one of these terms, remember what we're trying to do. I'm trying to figure out which one has the highest probability. Because they're all the same, I know that I can look in here and go, but it doesn't matter if I had 5, 10, 15, if I subtract 2 and then added 4, it doesn't matter. I mean, you can add constants and whatnot all day. As long as they're the same numbers for each one of them, it's not going to change the ordering. So therefore, since these are the same, I'm going to drop them. So if you drop those, you end up getting, so now the problem becomes finding the largest value between these three or K classes, however many you got, and then this thing in the book, this little delta K in the book, becomes natural log of pi K, x mu K sigma squared minus. So you get this little formula, and you assign x to the K, to the class K that maximizes this value. Very simple idea, but again, it took a little bit of math to get there, and sort of understanding that the ordering doesn't change based on getting rid of some things. But this is it. And why is it linear? Why is it called linear discriminant analysis? Because the x is linear, right? So this is just a constant, this is just a constant, and this is just a constant. Everything, so it's just x times some constant plus some constant minus some constant. So this function here is going to be linear in x. Okay. The next thing is, so we're going to stay with LDA, linear discriminant analysis, and now we're going to increase P, right? So in other words, right, that was all for P equals 1. So what did that allow us to do? It allowed us to use this single variable normal density function. I don't want to do that anymore. I'm going to let P be greater than 1. And if you do that, you get this multivariate Gaussian distribution, and you get something that looks like this. So use the same logic. You would come out with exactly the same equation. Matter of fact, let's just cover the equation before we go into what the covariance matrix looks like. So if you come up with it, use the same logic, you're going to come up with it. So get rid of the common terms, take natural log, and I'm going to put another parenthesis around here because I left out my parenthesis. So this is what we had before. Note that all you're doing now is using the linear algebra version of this, because now you have a vector x. So I have a vector x. My means are all a vector, and this covariance is no longer a number, but it's actually a matrix. So this is called the covariance matrix, and hopefully we'll see what that is here in a few seconds. But if you had data that look like this, where you'd have like a circle around it, you have a circle around this one, you have a circle around this one, where this represents an ellipse that's centered at some value for x. So in this case, you can see that I only have 2 predictor variables, x1 and x2, and then you can draw this thing out. If you get higher than that, it's going to be very difficult for me to draw that sucker. So right now we're just going to look at x1 and x2, and you can kind of see this thing coming off the, if the value of this density function were to come off of the page, it would come towards you, right? So it'd be kind of a multivariate function that would come up out of the paper or out of the screen. Let's see here. Oh, I wanted to kind of show the difference. So now this was P equals 1, and this is P greater than 1. So this works for any P greater than 1, right? So P 2, 3, 4, so on and so forth, you get this. So this is obviously just kind of comes right down. Well, the question is, well, how do you calculate this when they're vectors? And remember, the sigma squared is the variance. This is the covariance. So all I'm doing is putting the variance in the denominator by taking the inverse here. And how I multiply these two together, well, you do the transpose times mu k. So we would get a number there, and then we would do the same thing here with mu k. I'd have mu k transpose on one side, mu k on the other, and then sigma, the inverse sigma inverse covariance matrix, and then the negative 1/2 comes because you got the 2 there. So again, sigma squared is in the bottom. That's why you got taking it to the -1 power. And so this is the way that you would multiply it using matrix or linear algebra in order to calculate what these deltas are. Again, it's linear in x because you only have one x here, and all of these are just, there's going to be no terms that are squared. Next class, what we're going to do is we're going to take away that sigma squared. All the sigma squareds are equal to each other, and we're going to take away that assumption, and that's what we'll That's what we'll concentrate on. So then these two things right here will now become not linear in X anymore, but they'll become quadratic in X. So that's what we'll do in class next time. I think that's all I want to talk about. I mean, in class we did a little bit of Python to just show you some of the things that I talk about over here in yellow. But again, you can go to the course website and you can kind of see what those calculations are. I'll post what we did in class there so I don't waste anyone's time. But the idea behind this little calculation was to show you, like, if I had this data, well, what does that mean to have a covariance matrix that looks like this? You know, that's really the question. Why does this covariance matrix look like this? Why does this one look, it's a little long and skinny? That's the amount of probability at a particular contour line. So you could choose 0.9, 0.8, 0.7, whatever you wanted to, and that's what you would get. Okay, that's all I got. Hopefully you got something out of this one, and that's it.